Okay, so this is now the lecture notes or the final section of this course. And this is a bit less scientific, but a more practical, application-oriented part of the course, although there are some scientific points in between as well. So we have gone through a lot of physics and a little bit of chemistry of irradiation effects. Mainly this has been on the nanometer and micrometer size scales. And of course, this is all very interesting, but finally, if you think of a practical application, the question is what happens on human timescales. That is, what happens on a human time or length scale, which then affects somehow practical things. And what we are doing in this section is go through some examples of known macroscopic and application consequences of irradiation. I emphasize very much this is not by any means an exhaustive list. There are many, many other important cases, but we just go through some to give you a flavor. Even though I said that the nanoscale is not directly relevant to applications, this in a way is not true, especially in the semiconductor technology. Because in the current semiconductor technology, the transistors have become over the last decades more increasingly complicated. They are nothing like what you see in a textbook, some phrase, say the 1970s. They are complicated three-dimensional shapes, and the smallest features in modern transistors are well below 100 nanometers, so they are really nanoscale features. This is just one example of a so-called FinFET transistor. The details are not important. The point I wanted to make with this picture is just that we are really on the nanoscale in modern transistors. And now this starts to relate what you learned earlier on this course, because I showed you a number of heat spikes and collision cascades and showed that the typical collision cascade dimension can be easily of the order of 10 nanometers. So now you can easily imagine that if this is the active part of the transistor, if you happen to have a heavy, strong collision cascade right here, it will affect more or less the entire feature here. And if you have a collision cascade in the full active feature, it's easy to imagine that it may break. And fortunately, the probability is small. Of course, when you operate a normal semiconductor, you don't have any particle accelerator around. But on the other hand, there can be radioactive and always are radioactive impurities in the structures, and then there is also cosmic radiation which can penetrate the structures. So this means that one really has to consider these nanoscale radiation effects also for the practical applications. And as I said, this really is this list is not a comprehensive list of outcomes. So I'll start actually continue with this electronic effects. We just noted that they can cause errors in electronic circuits. This can be caused by cosmic rays or the radioactive decay anywhere in a circuit, and this is completely impossible to avoid. Even the best purification methods of materials cannot completely remove radioactive impurities. Moreover, the best purification methods cost a fortune, so one cannot really use them in a large-scale production. And then if you go to high radiation environments like space, nuclear reactors and particle accelerators, of course these issues will be worse. And an intermediate case is flights. If you go on a regular flight, they will have cosmic radiation, which at 10 kilometers is high up is much stronger than it is down at the ground level. Well, this issue that radiation can cause upsets in transistors in semiconductor circuits has been known for a good while. But now that the circuits have become smaller and smaller, this has become increasingly important. And these events cause single events causing irradiation effects, which cause then upsets in the electronic operation, are called single event upsets or single event effects on transistors. And these can further be divided into soft errors, which means that you change the state. For instance, a 0 becomes a 1 or a 1 becomes a 0 in a binary circuit, but the transistor continues to work, and next time you write, you get it back to the correct state. And then there is the hard error, which means that you permanently break the transistor and cannot repair it. And all of this is well known, and this has been considered for a long time, and especially for space, there is even a standard for testing against these different kinds of upset against. And it's also quite regular that you use particle accelerator to test against them, because it's expensive to shoot stuff up in space, and by the time you shoot it, you really want it to work up there. You can use particle accelerators with a somewhat similar radiation spectrum to test against them down on Earth. So the errors are impossible to avoid, so what to do? For memories, there is a standard correction scheme known as error correcting code. Um, and this means that you have to accept that there are errors, but then you build your transistor to have extra bits, and then use what's known in computer science as an error correcting code algorithm, used to make sure that even if one bit is wrong, you still get the correct answer. And this is something, if you have read a bit more computer science, you will run across this. This is a standard computer science thing, that if you want to store a standard byte, which consists of 8 bits, you can use a few extra redundant bits in an algorithm, which means that even if one bit goes wrong, you still get the correct answer. The most common variety, or basic variety, is the Hamming code, which allows for detecting 1 or 2 bit error detection. And this has been going on for a long time. By now, actually, the error correcting codes are very advanced and very big chunks of data. So already some more than 10 years ago, a technical report discussed 8 kilobyte data blocks. So you handle 8 kilobytes as one data block, and then have an error correcting code which allows certain error rate in this code and still give the correct result. This is a plot for one example where what you see here is the application bit error rate. You see it goes from 10 to the minus 1 to 10 to the minus 25. And then they set that target error rate zone, which is where they operate, where the circuitry is operated. So basically what this means is that all flash memories have these error correction codes. The designers know they don't work. There will always be a number of broken bits, and using this error correcting code, one can then detect an interval of acceptable error rates, which in this case was something between 10 to minus 11 and 10 to minus 19. 10 to minus 11 may at first sound a little, but remember, a regular flash memory now can be tens of gigabytes, so that's hundreds of gigabits. And 100 gigabits is already 10 to the power of 11 bits. So this 10 to the minus 11 is actually already a modern memories is already a significant error rate. So the basic message is that all the regular memories you use, they don't fully work. They have broken a number of broken bits, and then but they are built in a way that they automatically correct for these broken bits in a way that to the user it looks like it's a faultless operation. So this was a brief introduction to one thing which maybe is the commercially most important radiation effect, which is routinely corrected against. So it's actually a very important thing. and it's something all of us, when we use mobile phones and flash memories or computers, we use all the time. Well, then another set of important consequences of radiation are the mechanical properties. And now in this subsection we use mechanical properties in a rather broad sense to discuss a number of changes of the structural materials. And one of them, which has been studied a lot because of its importance in nuclear reactors, is the hardening and embrittlement of metals. And this I have already mentioned several times during the course. So roughly speaking, to recap, what happens is that when you irradiate a metal in here, this A is copper with before irradiation, B, C, D, E is after irradiation with 600 megaelectron protons. You see that what happens is that the stress-strain response changes dramatically. This starting part here means that the material becomes elastically harder, but then if you go to large strains, it also starts breaking. This point here means that the material completely breaks. Um, this is something which needs to be known and controlled when using metals in radiation environments. And as you can see, the effect is really quite strong. And here is another example for iron, which shows that how at already relatively low damage levels you change the yield stress, start changing the yield stress quite significantly. And this is the total allowed elongation, how brittle it is keeps going down. And the reason is indeed dislocations. These TM microgas show how you at already 0.01 dPa you have a quite high concentration of dislocation, then at 0.8 dPa some large dislocation, a quite complicated microstructure. Well, going on to other classes of materials in ionic materials, ceramics, one can have a very interesting other kind of response to mechanical response to irradiation. So what these graphs show is regular silica SiO2 on a silicon substrate after 4 MeV xenon irradiation from the top. So you have irradiated here from the top. And this was done on a structure where intentionally with lithography you had a trench of silica between two silica blocks. What you see is quite interesting, that when you keep irradiating, this initially sharp feature starts elongating and actually eventually broadens a lot, while it sometimes becomes less thick. So essentially what you do is this, the irradiation makes the material flow sidewise. And this is this effect flow due to ion irradiation is known as ion hammering. The idea is that ions act like hammers and make them flow. And this is to emphasize that SiO2 is otherwise quite inert material, so this certainly would not happen without the irradiation. And the basic idea of this is that the swift heavy ion causes a horizontal expanding shock wave. So the idea is that you have a high energy ion track, swift heavy ion track, which leads to a pressure wave, and the pressure wave expands, and this pressure wave then presses the material sidewise. Each individual track, the effect is quite weak, but when you have thousands of overlapping tracks, eventually this sums up to a significant effect. And this flow effect has also described with an analytical theory by Trinkaus, so one could say that at least on a qualitative level it's fairly well understood. And this goes also for regular silicon, and actually for a regular silicon the stress response is quite interesting actually. This plot shows here the in-plane compressive stress during amorphization. So what happens, start with crystalline silicon, you, as we know, start amorphizing it. When you amorphize it, you create interstitials and amorphous pockets, and these make build up a compressive stress because they want to expand. But then when you are fully amorphous, then you start getting this radiation enhanced flow, and then the stress actually goes down. So essentially what happens is that if you do this on a thin layer, that the silicon will first expand like this and then go backwards, the silicon wafer, when you keep irradiating. And I could also mention organic materials, as organic materials again behave very differently. The basic effect usually is that hydrogen starts leaving the sample, because hydrogen is most weakly bond, and it can react with the oxygen and nitrogen to form either hydrogen gas or H2O water, or other gases, and these gases then eventually outgas from the sample. So you start getting rid of the water and sometimes the hydrogen and sometimes the oxygen as well. But the carbon is most strongly bound. It's less likely that it leaves. So what typically happens during irradiation of organic sample is that the carbon content increases, so the material carbonizes, and a simple example of what this means in practice is that if you take regular paper and put it in an accelerator, after you radiate for a while, where you radiate it, the paper turns brown. At the same time, it usually also becomes mechanically brittle, because amorphous carbon is a brittle material. Actually, this fact that paper turns brown is sometimes used to figure out where your ion beam is. If you don't know it accurately, otherwise you can test it by putting in a piece of paper, then irradiating, and then check where you got the brown spot in the piece of paper. And now going on, I'll also mention surface effects. What happens at the irradiation when you at surfaces when you irradiate them. And especially for ion irradiation, this is quite important, because ion irradiation typically does not penetrate very deep, so the surface effects often dominate. And one well-known effect which happens especially when you irradiate to high fluencies by gas atoms is known as blistering. That is, you start forming bubbles due to the gas below the surface, and these can grow and bend the surface completely. You get these quite ugly blister-looking features, and the name really comes from blisters on the skin. So it really is an analogy to the blisters you can get on the skin if you have had way too much sun, or if you have had some smallpox disease or other disease. These blisters are gas bubbles which are filled with gas, and eventually they rupture if you keep irradiating long enough. But this of course usually is bad, but it turns out that one can actually use this for a beneficial effect. That is, that if you irradiate deep enough, and typically with hydrogen, the hydrogen goes in a fairly high energy MeV hydrogen. It's a fairly narrow range distribution, so you get most of the hydrogen in a fairly narrow depth region. What you may get is an effect like this, that you build up a hydrogen bubble, but then if you irradiate in a wide area, this sidewise area may be much larger than the lid, and then you can lift off essentially a lid of the material, pop up from the material due to the hydrogen bubble. And this is known as exfoliation, and can be actually a useful way of materials processing. And in particular, this can be used in silicon wafer manufacturing on a macroscopic scale. This was a method known as smart cut, which basically is exfoliation. This smart cut was a selling name which Michel Bruel, who invented the method, took into use to sell it better. So what he and his co-workers did is they implant hydrogen or helium on a silicon wafer at a high energy, so you get everywhere a deep layer, and then when you heat it up a little bit, you get this blistering effect. So you can get rid of a lid of silicon, so you can get a layer of silicon which is actually rather thin, but then but still almost perfectly flat. And then when you polish it and etch it, you can use this to get a thin layer of silicon, which can be placed on another substrate. So this basically was used as a way to make silicon on insulators that you bonded this silicon on a buried silica layer, and then you get a thin, you can get Si with this red thin silica layer below it, which is quite good for having an insulator layer below your active silicon layers. And this is actually a logical place to finish this set of lecture notes before we go into the electronic properties.